Deadlock management. Strategies for system stability. Introduction to deadlock. In a multitasking computer system, multiple processes often compete for a finite number of resources, such as printers, memory space, and CPU cycles. A deadlock occurs when a set of these processes enters a permanent waiting state, because each process is waiting for a resource that is held by another process within the same set. The inability of any process in the set to proceed brings the entire system to a standstill, which is a major concern for system stability and performance. Four conditions must exist for a deadlock to occur: mutual exclusion, hold and wait, no preemption, and circular wait. Mutual exclusion means a resource is non-shareable. Hold and wait means a process holds one resource while waiting for another. No preemption means resources cannot be forcibly taken. Circular wait means a chain of processes exists where each waits for the next resource. Operating systems manage deadlocks through prevention, avoidance, detection, and recovery. Deadlock prevention. Deadlock prevention aims to ensure at least one of the four necessary conditions is never met. This can involve making resources shareable, violating mutual exclusion, though often not possible for all resources, requiring processes to request all resources at once, or release all held resources before requesting new ones, violating hold and wait, allowing the system to preempt resources, violating no preemption, feasible for certain resources, or imposing and ordering on resource requests, violating circular wait, a practical method. Deadlock avoidance. Deadlock avoidance allows the conditions for deadlock to exist, but ensures the system never enters an unsafe state where a deadlock is possible. This requires knowing the maximum resource needs of each process. A system is safe if there's a sequence allowing all processes to complete without deadlock. Algorithms like the Banker's algorithm for multiple resource instances and the resource allocation graph algorithm for single instances are used to check for safe states before granting resource requests. Deadlock detection is a reactive approach that identifies deadlocks after they occur. This is useful when deadlocks are rare. A wait for graph can detect cycles indicating deadlock in single-instance resource systems. For multiple instances, an algorithm similar to the Banker's safety algorithm is used periodically to identify deadlocked processes. Detection can be triggered by denied resource requests or at intervals. Deadlock recovery mechanisms resolve detected deadlocks to restore system functionality. Options include terminating all deadlocked processes, costly, or terminating processes one by one until the deadlock is broken, using criteria to select a victim. Another approach is resource preemption, where resources are taken from one process and given to another, often requiring process rollback to a safe state. Starvation prevention is needed to avoid repeatedly targeting the same process. Conclusion. Choosing a deadlock management strategy involves balancing overhead and deadlock risk. Prevention is strict but guarantees no deadlocks. Avoidance is more flexible but requires prior knowledge and more overhead than prevention. Detection and recovery are reactive and involve recovery costs but are efficient for infrequent deadlocks. Many systems use a combination of these or may even ignore the